Good morning, superhumans! Now, just before I get into things, there is something I haven't done for a little while, so I'll do it now. I acknowledge the traditional owners of this land. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. So, I've got a couple of things to do today. I've got some stuff set up on the bench. I'm going to do a bit of a live demo based on that thing that you can see up there, which some of you may have seen on video already, and also a okay. Adam just asked a question about the standalone chip for the WS2812. That is exactly what I'm going to talk about today. So alright, where to begin? And also, I've got a couple of questions in the... Oh, I've got the wrong description for the live stream title. Sorry, I'll fix that. So, I have a couple of questions for Q&A sort of stuff, but I'm going to start by doing a demo and show you a little spreadsheet that I find quite useful personally, and then we'll get into Q&A after that. So if you've got questions, either for the things I'm about to show you or for other projects, queue them up, chuck them into the chat, and we will get back to it soon. So, I'm a little bit discombobulated because this morning I thought I'm going to do a live demo and show how something works, and I plugged it in the same as I've done in the past, and it didn't work. And it was up till I think about 3 or 4 minutes before I was due to go live, and I finally got it working. And the reason it wasn't working was I had a jumper wire plugged into the wrong pin. Sometimes you can't see what's right in front of your face. So I switched it over, started working, so now we can do the demo. Yes, as Scott said, cue the squirrels. Squirrels everywhere. Alright, let's just make a little bit of room since I left myself with a mess as I was frantically trying to get this working. Alright, so I just uploaded a video overnight showing making this particular thing, which was just a silly little project that I was doing. I had big ambitions for making the whole logo out of PCBs, and that went very seriously wrong, but I'm still going to be able to recover it. I have the panel that I made, and I can patch it with some replacement PCBs, and I'll CNC machine it and get it working properly again, and then I'll mount that over that thing. So the blue logo that you can see there is just cut out of a piece of core flute that I spray painted blue. So what I'm going to do is fix the PCB version of that directly on the front, and hopefully that will look kind of funky. So now I'm a real YouTuber with a backlit logo. Now, when I was starting that project, my original idea was that I would just get a bunch of LED strip, which would be addressable LEDs, like, just going to wave this one around because this is what I ended up using. This is LED strip with an adhesive back on it, and you can get it in a couple of different types. One is where the LEDs are just RGB LEDs, and what you got control over is red, green and blue for the entire strip combined. And the other type is where each of the LEDs is individually addressable, which means you can do things like run rainbow patterns down them, or basically set every LED to a unique color. I ordered the wrong thing. I ordered the simple one, which is all of the LEDs just being simple RGB LEDs. So I needed to figure out a simple way to control them. And a couple of years ago, I designed a little module which does exactly that job. So I'm just going to switch to Eagle for a moment and show you the design for this. Where am I? Desktop. That's what I want. Alright, so my general idea, backing up the story a little bit, an RGB LED, like an addressable RGB LED, often called neopixels or whatever, is a regular RGB LED that has got a little controller chip embedded within it. So what they do is they take the die for the controller chip, and put it physically inside the same package. So when you are sending the control signal to it, you're talking to the controller chip, and the controller chip is acting as a constant current driver for however many color channels are in the LED. So it might be RGB, it could be RGBW, or whatever. And so what you can do, well, before they were embedded in the chip, and World Semi is the company that really took this to the next level and popularized the whole thing. What they did was they started by making the controller chips and selling them just as a standalone package. So you would buy the IC and then connect it to your LED as two separate devices. And so they did a few different versions of it. The one where it really took off was called the WS2811, and that is the so that chip became really quite popular. And then fairly quickly what they did was integrate a slightly updated version of the WS2811 directly into the chip, into the LED, and we got the WS2812. Now there are multiple variations. I'm giving you a dramatically simplified version of the story. There was also a predecessor to the WS2811, which was I think it was the 2801, I can't remember. Anyway, I used to sell a module with that on it. So what I wanted to be able to do was control high power loads, and by high power I just mean things like big LEDs or relays, as if they are, I'm going to use the term neopixels because that's what everybody uses, even though that's just an Adafruit brand name for the generic part. So what I wanted to do was be able to connect a device like a relay to a microcontroller, or a whole string of relays, and then control them as if they are neopixels. So from the software point of view, it can't tell the difference. So what I did was design two little modules. There is the free NFET and the free NFET 3. This is the schematic for the 3-channel version. And what you can see down here is the WS2811, which is the little driver chip, almost the same as what is in a NeoPixel or a WS2812B. And so you can see it's got power and ground. It's got the 3 outputs, so RGB outputs, and it's got a pin for setting the speed mode, so you can put it into low speed mode or high speed mode, and then it's got data in and data out. So if you've set up anything ever with NeoPixels, you'd be familiar with the way you need to connect ground and power, and then you have data in coming in one side, data out coming through on the other side, and then data out goes to the data in of the next one, and you can just build a whole long chain of them. So here we've got the D in and DO for data in and data out. And what you can see is on the left side, we've got the data in connection, comes up to the D in, and then data out just loops out and comes across to a matching connector on the other end, which has got data out. So in a similar way to being able to daisy chain NeoPixels, with these modules you can just daisy chain them, and from the software point of view it just looks like a string of NeoPixels. But the interesting thing is I kind of did something a little bit silly with these with these outputs. Now the outputs here are low side drivers for LEDs, and the idea is that what you would normally do is on output 1, for example, which is the red channel, you would normally have an LED connected between that pin and whatever your supply voltage is. So you can see here I've got a 1K resistor coming up to here, and I've got a 10K resistor up here. So what I did was, instead of putting an LED in, so normally there would be an LED right in this portion of the circuit here, and the driver chip is turning the LED on or off, and it can use, because it's got a constant current driver built into it, it can vary that so you can get different levels of illumination. And instead what I did was use it to drive a small N MOSFET, and I won't go into the details of this part of the circuit right now. It's not all that exciting or interesting. But basically what we've got here is the output of the LED driver. When it wants to turn the LED on, you can think of it essentially as shorting to ground. And I'm going to give you a good demonstration of that in just a moment on the workbench. So you've got your load with your positive supply to it, and ground is disconnected. But then if you connect ground, the load turns on. So that's how those outputs work. It's the opposite to the way you would typically think of an output in terms of driving high or low. In this case, when it's on, it's sinking current. So it's pulling that side of the load low. So when out 1, for example, is turned on, just imagine it's turned on hard, you can think of that as being shorted to ground. And what it's doing is through this 1K resistor, it is pulling the gate on this MOSFET low. Oops, excuse me. And when it is turned off, no, I think I'm misexplaining this, so I'm going to stop before I send you all totally down the garden path. But, oh no, that is right. Yeah, because it's acting as an inverter. So when the output is off, so it's not pulling it low, what happens is the gate on this transistor goes high because it's being pulled up through this resistor, and it turns on. Now, being turned on, it pulls the gate of this MOSFET low, which turns it off. So what we've got here is this transistor, Q4, is acting as an inverter, driving this transistor, Q1, which is actually controlling the load. Now, all of this is probably a little bit confusing. So what we've got here is a big connection called drain, or D1, and this is where you can connect an external load on the negative side. This is probably going to make a whole lot more sense once I show it to you actually physically wired up on the workbench. We're going to see all of that in just a moment. And then that circuit just repeats. So you can see that we've got 3 sets of the same thing. I'll just see if I can highlight this here. So we've got that chunk of the circuit, which is, excuse me, which is for one of the color channels. And then we've got the same thing here, which is another chunk of the circuit. That's for another color channel. And then this final one here, excluding that source connection there, that's a different thing. That source connection is like a common ground for whatever power supply you've got connected to all of this. And let's have a look at the PCB version, PCB layout. You'll see this in probably in a lot more detail. What have I got? I've got everything turned on the wrong way. Don't want any of that. Okay, that'll do. So you can see the 3 big N MOSFETs here which drive the loads with their drain connections, and this is a double-sided design, so it's got those 3 big MOSFETs on the front of the board, and then on the back, if we flip it over and switch to the bottom track, or bottom mode, and go into single layer mode, this is where the little control transistors are. So these are the ones that are acting as inverters, controlling the main MOSFETs coming off the driver chip. And the driver chip is down here. So this driver chip, which is what, who was it? Someone was just asking about that. That is a WS2811. And if you look that up, you should be able to find it. They're pretty easy to get. Sold in very, very large quantities, or at least they used to be. They're probably not that common anymore because everybody uses the versions that's built into the LEDs. So let's have a quick look at how this works. I'm going to switch over to the workbench. So this is a little demo. Hopefully the audio is still okay. I'll speak up. I'm not using the radio microphone today, so if I move away from the computer, you won't hear it so clearly. Now this is a 30 watt RGB LED that I got at a market in Waichang Bay in China, and so it's Common, it's 32 volts. Common positive comes in here, and then it's got R, G, and B connections on here, which are on the low side. So it's common anode, and then we've got 3 cathodes, one for each of the colors. So essentially it's like 3 LEDs. In fact, if you look at the front of it, you can see a series of dots, and there are 3 rows of dots. It's actually rows of LEDs, so there will be, there's a row for each color. And I've got this soldered on here for now, but this is the little module we're going to look at. This is what I was just showing you. So if I hold it like that, that's aligned. Whoop, where are we? See if I can get it up in front of the camera. So that module is what you can see there in Eagle, just beside it. And you can see the 3 big MOSFETs, which are rated to 20 amps each, I think, 60 volts, 20 amps. So I can switch pretty high power load, depending on cooling. And if I turn it around, you can see the parts on the back. It's got the WS2811, which is the driver, and then the switching transistors acting as inverters. But what I'm going to do is power this up without even using the module. I'm just going to power up this big RGB LED. So I've got a couple of bench power supplies here. And the way I'm going to do this, to demonstrate the low side switching, is we've got 32 volts on this bench power supply. I'll just turn that on. It's all set. Got to make sure I've got the right voltage here. And so what you can see is right now I've got 32 volts across these connections, and I've got the positive side going to the common anode on the RGB LED. Sorry, my throat's not feeling too good today. And so I've got the ground connection here, well, the 0 volt connection essentially from the power supply. If I connect that directly to, say, the R lead, you'll see that the red LED will illuminate, and it'll burn your retinas with the force of 1,000 suns. So if we touch G, the green one, we get green, and if we touch blue, we get blue. So we've got positive coming in, and then by connecting the ground side or the cathode side of any of these, we can turn on the LED. And when you look at it like this, you can see that is what this module is doing. If I reorient this so that it's logical the way a circuit is normally set up, you can see we've got positive coming in at the top, as it always should be, and then going down through the 3 LEDs, going down to the module, and we've got the 3 MOSFETs, and those MOSFETs are switching to ground. So with this connected on here, nothing is going to happen because we've got no control over this module right now. But you can think of it as being, imagine having 3 relays here, and each of these relays can switch to ground on the cathode side of the LED to turn on any of those particular color elements. So how do we control this? Well, we can control this with something like an ESP8266, because as far as the microcontroller is concerned, it's just like a NeoPixel. This module with the WS2811 appears to be an addressable RGB LED. It doesn't matter what it's switching. In this case, we do have it connected to an RGB LED, but it could be switching 3 relays, it could be doing anything, doesn't matter. So over here, I have a WeMOS D1 Mini with a few random leads hanging off it, as you can see. So what I'm going to do is connect the driver module, and the connections that I've got are ground. So there is a ground pin coming off the module that goes to ground on the D1 Mini. Then I've got a data pin, and that comes, where is it? It's fallen out. D should be into, oh hang on, no, it hasn't fallen out, it's the other one. It is the orange pin. So the orange pin here is the data pin that goes into D in on here, and then these 2 are for a 5 volt supply. And I'm doing this so that it is totally disconnected from the computer, it's not doing anything else, and you can see that I've got no USB or anything. So what I'm going to do is connect. I've got another power supply, another bench power supply coming over here, and this one is supplying 5 volts. So I'm going to connect up the common ground So there is a common ground connection here that goes to everything, including to the D1 Mini. And then I'm going to connect up 5 volts. I haven't got this power supply turned on yet, but once it's turned on, that is going to have 5 volts on it. So with all these jumper wires, this is starting to look a little bit like a mess. But what we've got is if you ignore the D1 Mini side of it, you can see that we've got power for the RGB LED going to the controller module and then to ground. And then we've got power going to the D1 Mini, which is 5 volts, and it's also powering the control module. So now I'll turn on the second power supply, and the D1 Mini is now powering up. So if you wanted to control this using a microcontroller, you could basically treat this in the exact same way that you would sorry, I was distracted. I saw some things in the comment there. I've got to try to stay on track. So you can control this from a software point of view in the exact same way as a NeoPixel. So you could use the Fast LED library, you could use the NeoPixel library, and there are others as well. So what I've done is loaded Tasmota onto that D1 Mini. And let me see if I can switch. Can I switch? Let's see. Why can't I? There it is. Alright, so this is the web interface on that particular D1 Mini so that I can control it. Now I'm just going to hit toggle and let's see if we get demo fail. Turn it on. Oh no, cool, we've got illumination. So by turning what I did, actually I'll back up a little bit. I'll go into configuration and configure module, and what I've done is on D2, which is GPIO 0, I'm going to switch to desktop here so you can see more clearly what's going on. What I've got is the module type is a generic, and I've got GPIO 4, which is D2 on a WeMOS D1 Mini. For its function, I just selected WS2812. So in this particular case, Tasmota thinks that it has got a NeoPixel attached to it. And there are a number of configuration options that you can give to it to tell it things like number of LEDs, and you can tell it to do different patterns and fades and things. And that's how that sign up there behind me is working. But all I did was select WS2812 and I saved it. And now when you go back to the main menu, Tasmota automatically displays this little slider thing here where it lets you select colors and level of illumination, level of, what is this one? So this is the hue, this one is the saturation, and this is the brightness. So HSV. And I'm just going to turn brightness way down for now. Turn that on. Oh, you can't even see it. We don't have the overhead. Let's go back to overhead, and if I I'll turn it so that it's visible but not too bright. Alright, so what you can see here is by toggling the output we can turn this RGB LED on and off using this module, and we can also change its brightness using this slider. And we can also change the saturation, and the saturation is how much color there is compared to white. That's probably a terrible explanation, but if I bring the saturation way back here, what it does is start mixing the other colors in so that it gets closer and closer to white. The idea is that you can take, if you think about no saturation as being just flat across think of it as bandwidth, I suppose. So you have just plain white, and then as the saturation increases, so you bring it up here, it becomes more and more saturated until it's just the pure color. Now I'm going to switch to blue here because it's a blue. Which one did I want? No, red, blue, or green. No, there was one that is Yeah, it's blue. So blue is the accurate one. And there is something strange going on here, which I'll just mention in passing. It's not that important. Earlier I said that the WS2811 is the driver chip that is inside the WS2812 LED. It's actually not quite that simple. There are many variations of the controller chips. They have different versions and like different numbers of output channels and different characteristics depending on whether they're for RGB or RGBW or whatever type of LED. And one thing that is different between the WS2811, which is what I've got on this module, and a WS2812, which is what I have configured in Tasmoda, is that they've swapped the red and the green channels. So you can see here on blue, I've got the hue set to just blue. So this is basically fully intense blue color. It is coming through as blue. But if I switch to green, you'll see that it's actually outputting red. And if I switch to red, you'll see that it's outputting green. That's trivial to fix in hardware because all I have to do is swap the red and the green leads. So down here, I could have just taken the red and the green outputs, swap those wires, and then all of this color mapping would be fine. But I left it going straight through because I wanted to show the direct correlation with the current flow coming from the positive side through the LED, down the wire, and through the MOSFET on the module that's switching it. So, yeah, so what this allows you to do is control anything you like. And that's actually why I did the, and there are timing differences as well. That's right. So there are different versions around. But luckily the WS2811 works just fine as a WS2812, apart from that channel mix-up thing. Yeah, so that, if I switch back to main camera, so what I've just shown you there is what is going on inside that logo. It's just a long bit of this LED strip, and I've just got the three channels, red, green and blue, connected to one of those modules with a D1 Mini, and it is just changing the color on the LED strip, cycling through different colors. Now, when I did this, in fact, let's see if the first one I did was the single channel version. I'm just going to pull that up. Here we go. Desktop, there. So this is the single channel version of that module, and I did this one first because my original idea was that what I wanted to do was make NeoPixel relays, and so what I did was I just took one of the channels. I can't even remember which it is. I think it might be the red channel. Let's have a look at the schematic and we'll find out soon enough. Yeah, it's the red channel. So if you think back to that schematic that we had open just a moment ago with the three output channels, this is just a simplified version of the same thing. It is a single high power MOSFET which is switchable on the red channel coming out of this WS2811. So my general idea was that what I would do is connect this module to something like a relay, and then I could address it like a NeoPixel. Now, the logical extension of that, what I had in my mind, and I think this might actually be a really stupid idea, was to use something like this inside my switchboards. Because at the moment, all of the lights in my house are controlled by relays that are mounted in the switchboards. And what I could do is attach one of these WS2811 driver chips to each of the relays and have the control line daisy chained. So what that means is that all of the lights in my house would effectively be NeoPixels, even though they are mains lights running off 240 volts and switched by the relays in the switchboard. I could then have a single data line and connect it to a microcontroller. And as long as I had some kind of a mapping, like I knew that the fourth neopixel in the string was the lights in the bathroom, then what you could do is maintain, in the control system you could have a variable that maintains the state of each of the outputs, and then if you wanted to toggle a light in one room, you would just change the state of that particular entry in your list of all of the things, push the data back out the same way that you update a string of neopixels, and you could turn the lights on and off. So single data line control of every light in the house. And that would really just turn my whole house into a big neopixel installation. And at the time I thought this could be kind of interesting and clever, but I don't know, it also seems a little bit silly, so I didn't end up doing it. Yeah. Alright. Oh, Trady Trev said, doesn't Modbus work on a similar method? So, not quite. Last week I mentioned Modbus and how I knew nothing about it. Since then I've actually looked up what Modbus is, and it is based on RS485 for transport. So RS485 is a multi-drop serial bus, and it doesn't quite work in the same way as something like NeoPixels. With NeoPixels you have a daisy chain, whereas with RS485 it's more like addressable devices along a shared bus. It's a bit of a different architecture, and it's also more based on serial communications sending specific messages, whereas with NeoPixels it's a protocol specifically designed just for that. It's really optimized just to send control signals to set RGB values to different devices down the string. Yeah. So, what else to talk about this? I don't know. Anyway, I just thought this was cool. This is one of those boards where, so I designed this in 2016, and you know, sometimes you have an idea for a project and you think, that is really clever. This is awesome. I'm going to use this for so many things. And then design it and don't use it. That was the case with this. I ended up designing the 1 and 3 channel versions and then did almost nothing with them. I've ended up selling a few of them. I'd really like to know what people are using them for. My guess is most likely just large RGB LEDs like I'm doing here. But I really don't know. So let's I'm trying to remember what the command is. What you can do is use either the console or MQTT to set different patterns, and there's a pattern running on that one. So this pattern is being generated entirely within Tasmoda. It's got a number of patterns that are preset, and you just send an MQTT command and it then just begins doing that pattern. And you can set things like whether it fades, the rate at which it runs through it, and various other things. Excuse me, my throat really isn't good today. Alright, so I saw that Scott asked whether the Gerbers are available, and not Gerbers specifically, but all the design files are available. So if we go to, what am I doing? I'm lost. Okay, if I switch, no, I'm going to switch back to here, and this is where you see how unplanned this is. If I was being clever, what I would be doing is showing you something that you can buy. So I could then sell a bunch of these, and this would all be just a big promo. But I'm not that organized. I have 0 stock of these right now, which means you can't buy them from me even if you want to. And so the URLs are just tron.cc/freeenfet3 or freeenfet. And if you come down here, design files, you will see that there is a link to GitHub, and all of the design files are on here. So it's got the board file, the schematic, and a little explanation of how it works. And you can, if you really want to, you can take those designs. But now that I've been talking about this, I really need to assemble a few more of these. These are actually really annoying to assemble because they're double-sided. So what I have to do is, if I bring this picture up, so what I have to do is put on the solder paste and a thermal set glue and put these MOSFETs on. So the MOSFETs go onto the board with the solder paste, but also just a little dab of glue that I put on under the body, right about under there, and then I run it through the reflow oven, which reflows the solder, but it also sets the thermal set glue, and those parts are then glued onto the PCB, not just soldered onto the PCB. Then I take the modules out of the reflow oven, turn them over, put more solder paste on the other side, and then fit all of these parts, and then I put it back through the reflow oven again. So it then reflows the top side of the board. Now the bottom side, of course, also becomes molten, and that's why I need to use the glue. It's so that the those high power MOSFETs that are then sitting on the bottom of the PCB are glued onto the PCB as it goes through the reflow oven, and they can't move or fall off. So the process of assembling these, for me, is kind of annoying, which I think is why I just haven't bothered assembling more of them. I need to do some. Okay. Let's, I'm going to see if there are any questions about this, because this is kind of a, I've just been talking for ages about the, about this and not paying any attention to the chat. So, just to summarize, so Adam said, what's the product code for the standalone WS2812 chip? So WS2811 is the thing to look for. And something that Andy sent to me through a back channel and told me I should mention is that a string of WS2812 are effectively a general purpose PWM mechanism. And also, not only can you drive other devices, you can read data off in 24-bit chunks and also inject new data in 24-bit chunks into the stream from an MPU or sensor. That is really cool. And he said that Lachlan, at our local hackerspace, Connected Community Hackerspace, Lachlan is one of the very long-standing members there, and I have a feeling he might be current president or former president or something. So Lachlan came up with a bunch of experiments based on this idea. That is something that I don't really know anything much about. But yeah, I would really like to figure out and find some more about that. So I'm going to follow that up and see what Lachlan has been doing. Lachlan is the treasurer, Andy just said. Okay, cool. I knew he was official. So yeah, if you've ever looked into the actual protocol of the way the data works with a WS2812 or any of that particular family of devices, it is a stream of data, and so it's being clocked at a certain speed. I think typically either 400 kilohertz or 800 kilohertz. Excuse me. But it's a string of data which represents values that are then mapped within each of the neopixels onto the output channels, whatever those channels are, and it daisy chains on, so it passes the data on. So the way we typically use something like neopixels is we have a whole string of devices that are identical, and you just treat them as if they're all the same thing. But based on what Andy was just saying in the chat, you don't have to do that. What you could do is you could have a device like a microcontroller in the string somewhere which pretends to be a NeoPixel, but it could do different things. So what it could do is take input from other sources, for example, and modify the data as it flows through on the fly. So you could do some really interesting tricks with that. Okay. All right, so Tiago asked why the 3 ground wires, and I think that other people have mentioned that. I will just show that again because this is a fairly important concept, and it's one of those things where it's easier to see it. Well, for the way I learn, I find it much easier to understand if I'm seeing something in a, what am I looking for? Oh, here, main menu. I'm going to turn that off so it's no longer blinding us, and in fact I'm going to disconnect all of this. So I'll turn off the 5-volt power supply. I'm going to disconnect this one entirely, disconnect the D1 Mini and take it away, and what we're left with here is the RGB LED. So we've got red, green and blue. You can think of it as being 3 separate LEDs. Positive is coming in through the top side, and then negative is at the other side. So if we totally ignore this module for now, in fact ignore those wires, just imagine that none of this was here, and imagine that this was a single color LED. We got positive coming in from here into the anode, and then the cathode, which is the negative side, is down the bottom. And if we think of it as being just a red LED, if we connect ground on this side, red turns on. If we connect it to the green one, green turns on, or blue, blue turns on. So think of that as being a simple LED, nothing more complicated than that. And the only difference, so what I could be doing, say I disconnect the positive side, and then I connect negative onto here. So when people first get into electronics, this is typically how they tend to think about circuits, because we're used to thinking about switching things from the positive side. If you take away the positive voltage, then the device turns off. If you apply the positive voltage, it turns on. That just seems logical. But you've got to think about it in terms of being a circuit. If we've got this connected, then we have a circuit. It's coming in from the positive side, through the LED, and back out through the negative side. You can break the circuit here, but you can also break the circuit down there. It makes no difference in terms of whether it's going to be illuminated. So what we're doing is we are controlling the circuit on the low side, and imagine that there was only a single channel here, so this is the negative side coming out of the LED, comes down to here, and then this is making or breaking the circuit. And then this transistor down here is just making or breaking the circuit on the negative side. That's all it is. And it's just, there are certain reasons that I won't go into right now why it is often, if not usually, better to switch on the negative side than to switch on the positive side. So in this case we've got a common anode, so we've got one positive side for all 3 LEDs, and then the LEDs have got separate negative sides or cathodes. Yeah, so when you see it built up like that in little steps, it starts to make more sense, and then progressively add more complications. So we start with the simple circuit through the LED, and then we control the negative side of the circuit using a transistor, and then we introduce the WS28, the D1 Mini, which is controlling the transistor, turning it on and off using the driver chip, the WS2811, and that's how it turns the LED on and off. So now it might be time to move on to another topic. All right. Oh no, there are a couple more questions. So Doug's asked, was the PCB size small for a reason? I don't know. I just made it no bigger than it needed to be. The reason for making it bigger would be, okay, I think that question might be in relation to why did I make it very small and double-sided instead of making it, say, twice the size and single-sided with all of the parts loaded on one side. My guess is that's the reason for the question. I'm trying to think about that. I'm trying to think of back to 4 years ago why I did it that way. I think it might be partly because all of this was inspired by a module from years and years ago. And let me see if that is, if there is information about it online, because I think I've just marked it as RGB. I think I've just marked it as being not available or retired. Here we go, yes. So this particular module was from way back in 2009 or so, 2010 perhaps. Oh, sorry, you're not looking at the right thing. I will switch that back over to the desktop. So this, and zoom in. So this is a module that that Freetronics released before Adafruit had done any NeoPixel stuff. This was before the concept of NeoPixels existed, and it was an RGB LED on one side, and then that controller chip, so the WS28. Oh, here it is. Yes, this is what I was referring to earlier. The WS2801 is an even earlier driver chip, and that was on the back of the module. And the idea was that this would make an addressable RGB LED, and and you could daisy chain them together. So it's kind of annoyingly backwards, but that's just the way that it worked. So we've got CK in, so that's clock in, and SDI, which is serial data in. And this particular, with the WS2801, it wasn't a single wire system like the modern systems are. It used 2 wires, so there was a clock and a data pin. And it comes in from the right side here, and it goes out on the left. So what you can do is take a bunch of these modules and string them together and make effectively a string of NeoPixels. But this was before NeoPixels existed. And so the way this module was designed, we wanted to make it physically small with the LED on the front and then hide all of the driver circuitry on the back. And that's why it's got just the LED exposed on the front, and on the back it's got the driver chip, the WS2801. So when I was doing the NFET version, and I started with the single channel NFET version, I think I was taking my inspiration from this and thinking of, if you look at this is conceptually very similar to the single channel NFET module, because all it's got is a big NFET in place of the RGB LED, and it's got the controller stuff on the back. It's just updated with the WS2811 instead of the 2801. So yeah, I could have just made it a single-sided module and made it twice the size, essentially. That would work. Maybe I made more work for myself than I needed to, which I've been known to do once or twice. And Frank asked, why not make the FETs through-hole? No, I didn't make them through-hole, so they would be easier to assemble on a pick-and-place machine. For these particular modules, when I'm assembling them myself, I put those big FETs on by hand. I don't use a pick-and-place machine for that. I use a pair of tweezers and sort of push it down to stick it into the glue. But when I think part of the idea was that if I was going to have this manufactured in a factory, they would want to use a they'd want to use a pick and place machine. And also, if you make it through hole, it messes up your ability to put parts on the other side of the board. And I wanted to have all of the other circuitry on the back of the PCB. So Jigsaw said, have you tried WLED? So I have not. Yeah, there was a comment here saying that Home Assistant WLED is a fast and feature-rich implementation of an ESP8266 ESP32 web server to control NeoPixel, etc. LEDs. No, I haven't used that. That does sound worth checking out. So, S. Leonhardt said, how long can the distance be in between the chips? Ooh, that is a really good question. And this really relates to that thing I was talking about earlier with the idea of using this in a switchboard so that you could turn a switchboard, like an entire switchboard worth of controllable channels, into a string of neopixels. And the short answer is I don't know. But one thing that is very interesting about the design of the WS28 series driver chips is that each chip has a driver on the output of the data line. So it has the input side where the data comes in, and that signal is being modulated by the preceding chip in the chain. And that means that if you have a string of neopixels, you don't get degradation of the signal over the length of the chain because the signal is being regenerated at every single step by every driver chip. So the driver chip receives the incoming message and then it uses its own internal mechanism to switch the output and drive that same message on its output. So and that's why you can have strings of like 1,000 neopixels and you're still getting the same high-speed data throughput and you're not getting any degradation of the signal at the end. So the question comes down to how long can the connection be between two neopixels or between two devices that are being controlled using something like this. And I don't know. I don't know what would happen if you had two devices separated by a length of wire stuck into an electrically noisy environment, like say inside an electrical switchboard. Maybe that would be a really bad idea. But I would love to know. So if anybody has done that sort of thing, by that sort of thing I mean link neopixels across long lengths of wire, can you have meters and meters of wire in between them, or do you have to have it to within like 10 centimeters? Or what is the limit? I don't know. It would be a bit of a trade-off because the longer you make the wire, the more susceptible it's going to be to noise, and you'll start getting errors in the data that is being passed through. So yeah. And Matt said, have you thought about adding dimming to your home automation system? Yes, I have. I've talked about this a little bit in the past, but not for a while. And doing dimming is something that I would like to do, but it hasn't really mattered to me. It falls into that category of, if this was something that was important to me, I would do something about it. But I just find in my own house, for our particular use case, we typically want lights on or off. We don't necessarily want to set them to 30% or something. And the lighting in places like the lounge room is set up so that if we're watching TV, which is typically when you would want to reduce the lighting a little bit, we have illuminated lights in the cabinetry. So we've got the TV mounted in a wall cabinet, which has open like shelves down the sides of it. And we've got lighting inside the cabinet so that it glows a little bit. And we've also got lighting behind us on a lamp. So often what we do is turn off the main lights in the lounge room and just have the cabinet illumination on and the lamp on. and that gives enough light that you can see and you can walk around with no problems, but it takes away the overhead light, which is what causes the glare on the screen. So it's one of those situations where I've thought about it a few times and there just hasn't been a strong reason to do it. It hasn't been a case of, oh yeah, it would be really nice if we could run low level illumination. It just hasn't mattered to me. So I will probably get to that at some point, but for now I'm just switching everything. That's also one of the reasons that I wanted to centralize control in the switchboard, because what I had in mind is that if I have all of the loads coming back into the switchboard, it gives me one central point where I can do lighting control using dimming or whatever other technology, whatever method I end up wanting to do. So what I've got is a row of DIN rail mounted relays. I could just unplug all of those relays and plug in some kind of a dimmable lighting control module, which could be something like a C-bus module, or it could be something else, Dynalight or whatever. Though the output from that dimming control module can then be used to control all of the lights through the house. Okay. Lee Jones asked a question that I saw after the live stream last week. Was it last week? I can't remember. When I did the live stream where I did the lab tour, there was a question about how deep is my desk and how do I pass the cables through. So I'm just looking around for a tape measure. There it is. So there are a couple of vital things here. One is the height of the desk, and this is a compromise. So I've got it set to 740 millimeters at the moment, and that is a compromise. So with a normal office desk, they tend to be a bit lower. I can't remember what the standard is, but I think it's something like 650 millimeters. If you look at a typical office desk, it's kind of low. Everything is quite down, and the desk, if you're sitting in a chair, is typically not much higher than your legs. Like your legs go under it, but there's not a huge gap. And if you look at something like a workbench in a workshop or an electronics laboratory or something, because people tend to move around more, and also you want the things that are on the bench up closer to you, they tend to be a lot higher. So what am I looking at here? Yeah, so like workshop benches and things are often like 850 or 900 millimeters high, which is significantly higher than an office desk. And because what I've got here is a multi-use system, I've got the computer right here where I'm sitting now, I've got the electronics bench here. I wanted to come up with some kind of a compromise, and so what I ended up doing was making it 740 millimeters high, which is higher than an office desk and lower than a workbench. Now, it might have actually been sensible to do a stepped system, so I could have had a low bench where my computer is, and then had it step up, and then a higher bench. But I wanted to keep it simple, so I just made it straight through, all the way. Now, in terms of the depth, it is 750 millimeters deep. So that's the distance from the back wall to the front of the bench. And I did, when I did that, I made that choice for a reason, and it was based on being able to reach things that are sitting. I wanted the desk to be as deep as possible to give me as much workspace as possible, but I still wanted to be able to reach things that were towards the back of it without having to really lean over and grab them. So that was really just a matter of sitting down and reaching forward and seeing how far I could reach comfortably, and that's how deep it ended up being. And then for cables going through it, I've drilled big holes. So I've got, what I did was use a hole saw, one of those big drill bits that's It's like a drill bit, but it's a thing about that big. It's like a tube with teeth around it. You put it in your drill and you can drill, 50mm holes or whatever size you need to do. They're commonly used for putting holes through doors for mounting door locks. So what I've done is put holes through it near, well, basically wherever it's useful. So I've got holes through behind my computer, and then I run USB cables down through it and power cables and everything. And I've got holes through it at different points along the bench. So it's as simple as that. Just drill a big hole, stick the wire through. Okay. Oh, Scott said, my desk is 760mm, which leaves exactly enough space underneath for my keyboard tray and my legs. Okay, so by keyboard tray, I assume that what you mean is the keyboard is on a little thing that slides out from under the desk. So you've got 760, what did I say mine was? I can't remember. 740mm. Yeah, so your bench surface is just slightly higher, but then there is the height of the keyboard tray, which would come out from underneath. So if you have a keyboard tray, you need to allow for that as well. Yes. Okay. What am I doing? In standard fashion, I've got an hour into this and I've got no idea what I'm talking about. Okay, now there were two specific things that I wanted to talk about today before I got on to general Q&A. And now we've spent the entire first half talking about point number 1. Luckily, point number 2 is much simpler. And I'm going to pull up where is it? Here it is. I'm going to pull up a thing on a web page and show you in just a second. Alright, so I just stuck up a blog post this morning. Where am I? There. Okay. I stuck up a blog post this morning because there were some comments yesterday on Twitter about relation to... Okay, the specific problem was that there was a post on Twitter about designing a project using an ESP32 and using an analog input, and then discovering that when you turn on Wi-Fi, the analog input stops working. And that is totally counterintuitive. It is not something that you would ever expect to happen. And it's one of those things that makes you go, what the hell is going on? Because you can have if you're developing a project and you've got some signal coming in that you're reading on your analog input, and then you're doing your coding and you're outputting values on the serial port, and you can see that the analog to digital converter is working, but then you add a bit more code and then add Wi-Fi, turn on Wi-Fi, and all of a sudden you're not getting values. Debugging that sort of problem is the sort of thing that will drive you to, I don't know, I don't want to say it. Yeah, so it's one of those things that once you know that little problem, you can avoid it. But if you don't know about it, debugging that problem is something that would break your mind, because it seems to be totally unrelated. You turn on Wi-Fi and now your analog to digital converter doesn't work, and you go, what the hell is going on? You turn Wi-Fi off and it starts working again. So as Sion, Unexpected Maker, put in the chat, ADC channel is used by radio calibration. Yes, so in order to do Wi-Fi and Bluetooth, the ESP32 obviously has radios built into it, and what it does is internally it uses ADC2 as part of its calibration process for managing the radios. So the result is that you cannot use analog inputs on any of the pins that use ADC2 if you have Wi-Fi turned on. Now, this is one of the things, and this is the reason I'm bringing this up, is that this is the specific gotcha that led to the Twitter conversation yesterday, which led to me publishing this spreadsheet. because that particular thing is something that I'd noticed in the past, and it's not the only gotcha. There are many different weird things to do with ESP32 pins, and ESP8266 for that matter. I mean, obviously there are the bootstrapping pins. Those are very well known, and many people have been caught out by trying to use GPIO 0 and not being able to figure out why the ESP32 won't boot properly. And it's because if you pull GPIO 0 low during startup, it will go into bootloader mode. Now that sort of thing is reasonably easy to figure out what's going on because it's well documented what GPIO 0 is doing. But for people who are just getting started with the ESP32, there are so many of these little catches that it can be really confusing trying to figure out what pins you can use for what purposes. So a couple of years ago now, I did this spreadsheet where I've listed all of the pins and whether they were okay to use for different purposes. And that little Twitter exchange is what led me to do this blog post. So if you go to the Superhouse site now, this post will be there. Might even be the most recent post. Can't remember if I did this or the other one most recently. And it's the ESP32 pin allocation spreadsheet. And if you click on the preview of the spreadsheet, it'll take you to it in Google Docs. And I've given public read-only access to this, so what you can do is come along and use this spreadsheet yourself. You can't modify it, but you can make a copy of it and use it for your own purposes. So the way I use this is when I'm starting a new project with an ESP32, I make a copy of this spreadsheet and then just for that particular project, and then I start filling in the details. Now, what I normally do is in the purpose column, I write what I'm going to be using that pin for. So I'm not going to mess around with this spreadsheet right now because I've published this as a template and I don't want to screw it up while other people are potentially copying it. But what it does is list, because this particular one is set up for a Vroom32 module because that's the module that I end up using very commonly, and it's got the pins for the Vroom32 in column A, and of course you could do a version of this for whatever module or the bare chip or whatever you like. The critical thing is that it's got the ESP32 pins here, so you can see GPIO 0 for example is on pin 23 on the ESP32, and if you happen to be using a Vroom32 module, that's pin 25 on the module, but a lot of the time you don't care about that. The important thing is these attributes across to the right, and I put notes in different things here, so if you just mouse over one of these, it'll tell you whatever caveats are attached to it. So for example, GPIO 0, it is pulled up typically because you want it to go into normal boot mode. If this is pulled down, then the ESP32 will go into bootloader mode. And you can use it as an output, but the caveat is that it outputs a PWM signal at boot up. So if you have a device which is connected to this and you are controlling it, and it could get an unexpected PWM signal when the chip is starting up and before any of your code is running. Which means if you have something like a servo connected to this pin or any device that uses PWM, and say you're controlling a robot, you can use GPIO 0 as an output, but whatever device is connected to it could move unexpectedly because you'll get whatever value is coming out of that at startup. After the device has started up, you can then use GPIO 0 as an output if you want to. I always avoid it because it raises too many possibilities for things to go badly wrong with not being able to boot if you're externally biasing that low for whatever reason. So other columns I've got here. This is the strap, so bootstrapping pins. these pins that have a red Y against them, so red for danger, stop, that means they are strapping pins, and they are used for setting the boot mode or setting some parameter of the ESP32 while it's booting. So these are the ones that should generally be avoided if you possibly can. And HAB stands for high at boot, and I put a little note there just to explain what the acronym means. So once again, if you have some kind of a device that is being controlled by your ESP32, say you're switching a transistor off one of these outputs, and that transistor controls something externally, when the ESP32 is booting, these pins marked as high at boot will either be constantly high or they will output some kind of signal. So, well, actually I should have put a caveat against that one, shouldn't I? Because it outputs PWM at boot. So these ones I've marked, I think, are constantly high at boot. So if you have output debug info at boot. So GPIO1, which is the TX pin, outputs debug info as the chip is booting. So once again, if you're controlling something off that pin, that thing is going to be going crazy as the ESP32 is booting up. UARTs, so we've got TX and RX pins here, and then we've got RX2, TX2, and CTS and RTS pins for, what is that, ready to send and clear to send, I think they stand for, so they're part of the old serial, like hardware handshaking. And digital analog converters, so I show that we've got DAC1 and DAC2 on those particular pins. And PWM is an important one. Well, I find it's important anyway, because I end up using PWM output a bit on different things. It's really useful for things like controlling servos, but other stuff as well. PWM is just generally useful. So it's very useful to know which pins you can safely select as PWM. And you can see here, what I've done is marked in the ADC column. You can see all of the ADC2 channels are marked in this sort of tan color, because you can use them, but with the big caveat that they don't work when Wi-Fi is in use, and when you're going to use an ESP32 without Wi-Fi. Not very often. It's one of its big selling points. So there's this note down here just saying, to really highlight it, saying ADC2 doesn't work when Wi-Fi is in use. But ADC1 is fine. So all of these channels that have got ADC1 associated with them, you can use those as analog inputs whether Wi-Fi is running or not. They're safe to use. But down here there are some other caveats. Okay, so as an input, these ones you can use as an input, but there is no pull up or pull down internally on the chip. And this has actually caught me out. In fact, I think this might be the thing that made me make this spreadsheet in the first place. It was a couple of years ago now. I was working on a project and I wanted to be able to read, I think I was reading button input. And so I had some buttons that were connected, and the usual way to do this is to have a button that connects, one side of the button connects to the digital input and the other side of the button connects to ground. And then what you do is in software, you turn on the input pull-up resistor on that input. So when the button is not being pressed, the input pull-up is pulling the input up towards 3.3 volts, and then when you press the button it goes down to 0 volts. So you can detect the transition from 3.3 volts to 0 volts, and that way you know when the button is being pressed. And if you don't put your own pull-ups on the outside of the chip somewhere, then typically you can use the internal pull-ups. It's a software command, you just turn them on, the pull-ups are activated, and everything is good. So I did this on a design, and I couldn't figure out why it was constantly thinking the button was being pressed. I was getting some kind of random input. Sometimes it'll be being pressed, sometimes it's not. Had me tearing my hair out, as you can see, and it took me a while to figure it out. And looking through the data sheet, I found a note saying that there were no input pull-ups or pull-downs on those particular inputs. So I then just added an external pull-up resistor and the project started working perfectly. And my lesson was learned, but then I had to revise the PCB. I think I ended up spinning a whole new PCB revision just for that. Because I had not noticed in the datasheet that those do not have input pull-ups or pull-downs. So, this is, yeah, so I ended up thinking, this is really frustrating. And the thing is that all of this information is in the ESP32 datasheet. And of course, I'm talking specifically ESP32 here, but the exact same thing applies to ESP8266 and ESP8285 and ESP32S2. They all have special cases on some of their I/O that you need to take into account when you're designing your project. So I should do a version of this for the ESP8266 as well. I just haven't, because most of the time I end up using an ESP32. You might think those are the only two processors I ever use, and I do use other processors. There are quite a few different CPUs that I use, or MCUs that I use in different projects. So where are we? Output. Okay, so the other caveat is that GPIO 34 to 39 you cannot use as outputs. You can try doing, you can try writing to them as outputs. Nothing will happen. So those particular 4 pins are quite special case. They're fine for analog input. They're fine for digital input if you apply your own bias to it, but there's no input pull up or pull down, and you can't drive them as outputs. So the way I typically use this, as I mentioned earlier, I start with this as a template. I make a copy of it for the project that I'm doing. And then my next step is to look at all of the things I need to connect. So I look at any inputs I might need from, say, buttons like user interface, for analog inputs, and then I tend to prioritize them. So what I'll do is, if I need analog inputs, I will generally go down here and apply them to these pins 34 to 39, and in here for the purpose, then I just type in what the purpose is that I'm using in that project. Because if I end up using another analog input, like say GPIO 32, and I think, oh yeah, that one is my first available 8AC1 channel, so I'll just use that for my analog input. But that has now used up an input which is fine for digital input, and that has pull-ups and pull-downs in the processor. So then later, if I find I need a digital input for a button, like say I want to put a control button on the project somewhere, I might only have, say, GPIO 34 or 35 left, and they've got no input pull-ups. So doing this pin assignment is a matter of prioritizing the different things that you want to connect to the processor, and then figuring out how you're going to assign them. So I start by prioritizing assigning analog input onto these 4 here, because those aren't a whole lot of use for other things except digital inputs with external pull-ups. And then there are certain things that I typically assign. For example, just about every project I do seems to have I2C in it somehow. Like often there are sensors, I might have environmental sensors, or something might be a little OLED. Those little I2C OLEDs are awesome to add to projects to give you some kind of a debugging or status output. The very small OLEDs, they might only cost $2. Like it is mind-boggling how cheap you can get little displays for these days. A little monochrome I2C OLED in like a 0.9, what sizes? There's a 0.91 inch, I think what's the resolution? 128 by 32. They're very small. They're like this big, and the text that you can put on them is quite small. So it's not the sort of thing that you would use as a a regular user interface. But for configuration information, say you were making a little IoT type project and you want it to boot up, and then you want to be able to see what IP address you've been assigned on the network so that you can then connect into it. It's perfect for that. I put a little $2 or $3 OLED on a project, and when your project boots up, it can display its information on the OLED. Fantastic. So I typically find that what I'll do is I will go in here and say the I2C pins, SDA, SCL, they're pretty much always taken. Every project I do, I'll just assign them and I'll say SCL, SDA. And then TX and RX are often used as well because they are typically connected to something like a USB to serial converter or whatever. And then I will quickly block out the really obvious things that I know that I'm going to need. So I2C gets blocked out, TX and RX get blocked out. Often if I'm using SPI, then those pins will get blocked out. And by the time you've done that, it's actually taken away a whole lot of I/O pins and reduced your options in terms of what you are going to assign to the specifics of your project. So that's when it really gets into the next stage of looking at what pins are still left and what your needs are, and then mapping it. So have at it. If that spreadsheet is useful to you, go for it. And if you've got suggestions for improvements, oh, one other thing, sorry, I forgot to mention. This list looks very short. Like if you look at this this list of things here, and that is because there are hidden rows. Now you'll see over on the left here, these little expose or these expose buttons. I'm going to click one here and expose it. There are extra rows in here which are pins on the ESP32. I actually haven't written them in here. I should fill that detail in. But these are extra I/O. So GPIO 4 and 5 are commonly used, but 6, 7, 8, these pins are on the they're used for things like SPI flash. And so what I've done is put all of those pins in the spreadsheet, all those I/O signals at least. And if you want to see them, you can just unhide the rows. And there are more hidden rows down here. So if I unhide all of these, but they're highlighted in red so that you know these are in the danger, don't touch zone. So if we expand all of the rows, that's a more complete view of all of the signals on the ESP32. So you can see GPIO from 0. Should be a complete list, I think. How many have we got? So it goes down to 39, and it's on row 41. So yeah, starting from 0, and we lose 1 row for the headers. So that is every I/O signal on the ESP32, including the ones that you can't use. And there are some here, like I've specifically marked these as not broken out on the Vroom because this particular spreadsheet is most commonly used for projects that use the Vroom. So I'm just going to hide these rows again. If you do want that information, it is there. And what I should do is I'm going to go back and, sorry, I'm being very slow doing this because I'm talking and thinking at the same time, which is not something I'm good at. So what I'll do is go back and fill in some of the detail in relation to these hidden rows because that could be useful. And it might be worth expanding this, adding some more columns for other types of modules so that you can use it for whatever your project is. So you can see here, for example, on rows 8 to 13, I've got the signal names here, GPIO 6, etc. But I don't have the ESP32 pin number, basically because I just don't care. It's those are used by the SPI flash, and that's not something that I want to mess around with. And I certainly can't use it for general purpose I/O. But so effectively, those are useless to me. So I just hide them. hydros. Boom, gone. And what that leaves you is the pins that you can use in your projects, with all of those caveats attached to them. And Tradie Trev said, I can understand why a lot of larger ESP devices have a side MCU to get some extra I/O. Mostly see it Wi-Fi circuit breakers, fan controllers, etc. Yeah, exactly. So the ESP32 is a very powerful MCU, and dual core. It's got Wi-Fi, Bluetooth, all the good stuff. But its I/O is a little bit strange. So what I tend to do is use things like, there's one project I'm working on. Okay, that one, the robot water cannon thing. I need lots of PWM on that, and so what I do is use an I2C PWM driver chip. So I'm not even bothering to do the PWM directly out of the ESP32. What I'm doing is just using I2C, communicating with the PWM driver, and then it generates all of the channels using hardware clocks and things. So I don't have to do it by trying to figure out how I'm going to get PWM out of this. Enough PWM. So if you look at the PWM column in this spreadsheet, there are quite a few PWM capable GPIOs, but most of them do other things. So if you've got I2C, then you lose these two. If you've got SPI, then you also lose those other three, so now you've lost 5 of them. And then we've got, well, those ones don't matter. Boot fail if pulled high, so we lose this one because it is a strapping pin. Well, you could use that one for PWM. But anyway, my point is that it looks like there are a whole lot of PWM pins if you just look down this column. But by the time you start knocking out the ones that are used for other purposes, you only end up with a few left. It's not that many. So using external I/O devices in combination with the ESP32 is, I think, really the way to go. So, Jason Perry asked, does anyone know if international shipping is turned on again in the store? The answer is kinda. International shipping is turned on, but the big problem right now, well, there are 2 problems. One is all of the economy international shipping is gone. That's just not being carried at all anymore by Australia Post, and all of the letter international shipping is gone. Now the thing is that letter international shipping is something that in the past has been really useful to me to offer, because a lot of modules and things that I sell, like this for example, it's in an anti-static bag with a card, and look how thin it is. It's super thin. This whole thing is about 4 millimeters thick. So I can slip this into a padded bag and send it as an international letter for, how much was it? I think it was about $3 or something for shipping. Very small. No, was it $2? Yeah, $3.30, something like that. So the actual cost of shipping something that is small, as long as it comes to less than 50 grams, was only a few dollars. And the problem is that international economy letters and packages are gone. We just can't ship out of Australia with that at all anymore. So that's a global problem. I can't send that to anyone anywhere using those methods, which means that you have to go up to the more expensive shipping methods, like what they call, so above international letter, there's economy, and then above economy there is what they call standard. Standard includes tracking and other nice things, but it means that the price goes from like $3 to $12 to $22. So instead of shipping one of these for $3, it costs me like $22 to post this, which is the cheapest I can send it international, and that is just a total killer. But beyond that, it's not just a matter of the price, it's also that many destinations can't be shipped to at all. And I had this situation a couple of weeks ago. I think I did a little bit of a rant about it, where I had a customer who placed an order, and he wanted it to, that's right, he ordered to be shipped to Oman. And Oman is not accepting packages from Australia Post at all anymore, like at any price. It doesn't matter what service you select. I just cannot ship to Oman. It's impossible. But I could ship to United Arab Emirates. So in this particular case, my customer arranged for a friend who was in the UAE to receive the package. So I shipped it to the UAE, and then his friend reshipped it from UAE to Oman. So that's the sort of rubbish that we have to put up with at the moment. So the short answer is yes, international shipping is turned on, but there are very limited options for what methods I can use. And I'm really sorry about that. I wish I could ship, but I just can't. Okay. Now, what have I been missing? There's probably stuff in the chat. All right, I have spent an hour and a half now talking about the 2 points, only two, that I thought would take maybe the first half hour of this live stream. So, oh, and I should mention, I put up a new video. I think I might have mentioned this at the start, I can't remember. The new video that just went up is just making this and showing all of the major failures that went into it. So, yeah. I was just going to say I'm going to have another video up soon, but I can't promise that because every time I promise it, it turns out that I'm lying. I will do my best. I've got the video. So on my air quality sensor mini-series, I've taken the detour into doing a video about setting up a data logging system with MQTT and all those sorts of things. And that is largely filmed. Actually, a lot of that now is I just need to do voiceover for it. And that is really, I don't like doing it. In fact, I don't like doing videos that are primarily showing software installation. It's a whole lot of sitting here with the screen recorder running while I click around and do things, and then just talk about what I'm doing. And it has to be terribly boring to watch, and it's boring and frustrating to do because it just takes so long, and recording the voiceover and trying to sync it up and then cutting little clips out of moving stuff around on the screen, and there's nothing really showing except stuff on the screen. I don't like doing those sorts of videos, but they can be useful, I suppose. So I've got to finish that one off, and then I can do the next air quality sensor thing, because the next episode of the air quality sensor mini-series is dependent on me finishing the one about setting up the data logging system. If I don't show that first, the next one's not going to make sense. Now, oh, John said, it looks like my t-shirt has a hole in its roof. Yeah, it's where the rain comes in. I've got, I have 3 of these t-shirts. I ordered one originally just to see how it would turn out, and that one is quite old, so the logo on it is faded to the point of being barely legible. And the others, this one has got like a little manufacturing glitch on it. It came like this when I bought it, and the other one has got marks on it as well. In fact, the weird thing is that I ordered a shirt. I can't remember where this came from. I think it might have been Spreadshirt. I ordered one, and it's got the design on the front, and it's got the URL on the back, and the t-shirts arrived, and they put the URL on the back, and they just forgotten to print the logo on the front. So I've got a version of this shirt which is just blank on the front. Okay, so alrighty, a couple of interesting questions coming through. Yay! Now, so Daryl had a question related to the lab tour. How do you store your SMTP components once they are out of the tape but not used? Okay, now I have a couple of solutions to that, none of which are particularly good. So I have, let me see, how do I do this? I've got reels of parts. I've got reels that are fixed to the pick and place machine. I've got spare reels which are sitting in plastic tubs. I've also got reels that are on little dispensers. I'm going to grab one. So these are little aluminium mounts. You stick a reel in here and you can feed it through. So the idea is this is used for manual pick and place. You have this sitting on your bench, you peel the cover back, and what you can do is just pull the tape down and expose more parts and pick them up from here. So it's a convenient way of having, in this case, up to 5 reels sitting in a bench top dispenser. So I have a couple of these little dispenser things sitting over there as well. This one's only got 1 reel in it right now. But then the next stage beyond a reel is cut tape, and most commonly I just have that rolled up and then put inside Ziploc bags, and I have that in another plastic container, and this is showing an embarrassing lack of organization, but you can see I've got a plastic container that says cut tapes. Kind of describes what's inside it. So, oops, get that off. And inside it's like a whole lot of anti-static bags with bits of tape that have been cut for specific purposes. I've even got some little loose things in here, all sorts of random stuff. And a lot of it is things that, in order to be able to find things quickly, I print labels and stick it on. So AMS 117 voltage regulators there. So this is, as you can see, lots and lots of bits of tape that are stuck aside for different purposes. And there's some tape with those big MOSFETs which go on the free NFET modules. Lots of things. But that's not indexed, it's all just a big grab bag of stuff, and I've got no idea what's in it other than based on my memory. So this is where I need Xeon's management system to keep track of all of my stock. So then so beyond cut tapes, and I think this might be getting to the crux of the question, how do you keep track of parts when they are out of the tape, so when they're loose? Right, so I've got things like resistor kits. This is 0603 resistors, and when I'm doing prototyping, this is the sort of thing I use. So each of these little compartments has different loose resistor values in it. If I'm hand assembling a prototype, typically what I'll do is I'll just pull out this kit and then I'll just grab the values I need, stick them on the PCB. So I don't bother pulling bits out of tape for that purpose. So I've got an 0603 resistor kit, there's an 0402 resistor kit, I'll stick those back, and then capacitor kit, so 0603 caps, 0402 caps, which way? Similar sort of idea, it's just lots and lots of little compartments, each one different values. So I bought this as an 0402 kit, and so yeah, you can see on the, if I can get some focus, you can see on the front here it's an 0402 capacitor kit, but the 0402 kit didn't use all of the holes in it. So what happened was that all of the values are populated down to this point, and then the rest of this was just an empty container. It just had all of these compartments. So what I did then was made up little stickers, and I put 0603 capacitors in this other section. So I've got a single kit that combines 0402 capacitors and 0603 capacitors. So, and all of this sits in these little shelves just directly above my workbench, so I can pull any of those down anytime I need them. Then I've got miscellaneous SMT, and this is something I thought would be really useful, and it turns out that I just barely use it. So I don't even know what it's doing sitting in a prime position above my bench. This is a thing I got down at the local craft store, and it's a whole lot of little containers inside a carry box. So it's a little bit like a tackle box sort of arrangement, except that instead of having fixed compartments, it's containers inside a bigger thing. And then in here I've got 2N7002, so transistors there, and they're inside a bag, a little Ziploc bag, which is inside the box. And 1N4004s loose, although I've got reels of these as well, and shotkeys and static protection. Oh, that one's empty. A bunch of NPN transistors in there. That's really all I've got in there. So what I had thought was that this would be useful for all of the things that don't go into my that aren't in the resistor kit and capacitor kit. This would be things like other diodes and transistors and whatever. But I think it's the design of this particular container. I just don't like it very much. I think it would probably be better if it was more like one of those other kits where it had all the fixed compartments just with doors instead of with containers that come in and out. And these containers are quite badly made, which means I can't use them for containing parts on their own. That's why I've got bags inside them. So this little container, it's got a door on it and you pop it open, but the problem is that if you pop it closed, there's a little gap around it, the lid wobbles, doesn't seal properly. So if you put like 0603 parts or anything in here, they're just going to come out through the gap. That's really useless at containing them. For the 1N4004s, because they're, I think what, SMA, they're very large. I have those loose in the container and I can close it and it's okay. I can turn it upside down and they don't fall out through the gap. But anything smaller than something like a power diode like that, and I have to put it inside a bag, which is why for the 2N7002 I've got a Ziploc bag inside the container, which kind of defeats the purpose of the container. It's disappointing. I wish there was something better for that. And that is why I've got that big plastic tub over there, which has got all of the cut tapes in it with all of the Ziploc bags and everything. And I think I just end up relying on that more. It ends up just being more practical. Yeah, Station 240 said a bag in a container in a box. Yeah, yes, it's 3 levels of of containerization. So I'm going to get back to the thing about the James's question about COVID, but just because it's on topic for this. So Sion said, that case is awesome. Where did you get them? Which case do you mean? Because this case I thought would be awesome, and it turns out that I don't think it's awesome. But if you do want this, I got this one at Spotlight, and I think they were reasonably cheap. The same company makes them in a few different sizes and different variations. The capacitor kit, this case is really nice. This is beautifully made. I can't remember how much this capacitor kit cost, but I don't think it was cheap. Can I get it open? I'm trying to open it facing away from myself. So yeah, this is a really nicely made case. These little things, I'll open this one because it's got nothing in it. These little lids clip open and then clip closed, and they are well designed so they seal properly. You can have 0402 parts in here, and I can turn this upside down, nothing's going to fall out. It's all good. So this is good quality. So getting back to James's question. James said, how has COVID impacted your consulting business versus your Freetronics/Superhouse store? All right. It has effectively killed the online stores, and it has made the consulting business go crazy, which is not what I was expecting. In fact, it's the exact opposite of what I was expecting. So when the first period of isolation began, so whenever it was, March, I think, I can't remember, there was a period of about 3 weeks when the online stores basically just stopped. It was like someone had flicked a switch and disabled the shopping cart or something. I would go days and days without getting a single order, and then I get one order and then go days and days without any orders again. And that is totally understandable, because early on there was a lot of uncertainty. People didn't know how long this was going to go on for. They didn't want to, they didn't know whether their jobs were safe. People still don't know whether their jobs are safe. And so that uncertainty meant that people didn't want to buy things. And that's 100% understandable. So if I just sat down and thought about the situation and tried to rationalize through it in my own mind, what I would think is that online businesses would boom and offline businesses and consulting and those sorts of things would die. What I've seen has been the opposite. And I think the reason that the online stores are having such a problem at the moment is it largely just comes down to fulfillment. And my orders now are almost exclusively Australian. Like, before all of this happened, the breakdown was probably, around 50-50, give or take. It would vary a bit one way or the other. So about half of my orders would come from Australia, about half of them would come from overseas. A lot through Europe, some through America, different places. Smaller amounts through Middle East and those sorts of areas. But at the moment, if I look at my order board, it is almost 100% Australian. And that largely just comes down to the fact that I can't ship anything overseas now for less than like $20. And that really just kills all of the small impulse buys. People don't want to spend $20-something just to pay for shipping on a small item, and then it may not even arrive for 2 months because everything is so uncertain. So the result is that my online store sales have really just taken a dive. For Australian sales, they're still pretty strong. They're doing well. In fact, I think in terms of, if you looked at just Australian sales in isolation, I think I'm doing at least as well as normal, maybe even a little bit better. So, but because of the loss of international sales, that has really killed a whole lot of things. So the other part of it is the consulting business. This is what I was expecting to totally fall over, and it hasn't. And in fact, I have more consulting work now than I've had ever. And that's actually one of the reasons as well over the last few months that videos I just haven't made progress on videos. So once again, trying to rationalize through this, what I thought would happen is that businesses would not want to invest in new development or new technology because of the uncertainty of the market and not knowing whether it'll be possible to sell things. But I think what's happened, or what I'm seeing happening as well, at least with the people that I'm working with, is businesses are seeing this, I'm not quite sure how to put this. I was going to say seeing it as an opportunity, but I think that's probably the wrong word. There, maybe a better way to put it would be, they're seeing it as a time where they have to do something or die. So the result is that I've actually got more people coming to me now for consulting work and saying, we want to, we've got this new product that we want to develop, or we want to take this to market and we need to design a control system for it or whatever. I've seen more of that in the last few months than I've ever seen, which is good. It puts a bit of pressure on in terms of being able to deliver things, and so I need to be careful about not overcommitting myself and being able to deliver on the things that I say I'm going to deliver. But the good thing is that it means that I generally have a bit of a queue of consulting work at the moment and design work to do for commercial clients, which is a nice thing to have. Right now, I'm actually in a bit of a limbo state because I have three consulting clients that I'm doing design work for who, so I ordered revisions on PCBs for all three clients, and they went to production, got a little bit delayed. They sat in China for nearly a week after the PCBs had been made before they ended up shipping. They're now in transit, so they're with DHL, and I need to check out where they are. But basically, I've been in this period where all three of those consulting projects hit a checkpoint where new PCBs needed to be fabricated, and all three of them are waiting on the exact same shipment with PCBs in it. So I've had a couple of weeks now where I've been kind of treading water on those three consulting projects. And then all three sets of PCBs are going to arrive in the same package, and then I'm going to be super busy again. So more consulting work in my very near future. Basically, as soon as I see the DHL van pull up on the screen up there, I'm going to be rushing to assemble a whole bunch of PCBs. Okay. Okay, so Burkett asked, which I2C expander do you use? There are two that I typically use as my common, just, reach for it and use that as a solution. One is the MCP23017, and I've used that in a bunch of things. I've used that in my new light switch controller. It's in the Relay 8. Just wondering if I should pull up some examples here. I don't think I will. It's already nearly 12 o'clock. So for general, essentially for I2C controlled GPIO, I use the MCP23017. What that gives you is two banks of 8 I/O pins, which can be digital inputs or outputs, and then you can daisy chain them. So you can have up to 8 of those chips on a single I2C bus. Well, not daisy chain, it's the wrong way of putting it. It's got 3 address pins. So 2 to the power of 3 is 8, so you can have up to 8 of those chips on your same I2C bus, each one of which gives you a total of 16 digital inputs or outputs. So with a single I2C bus, you can control a whole lot of I/O using the MCP23017. And I've used that on many, many things over the years. It's generally been very reliable. In fact, I'm struggling to think of a situation where it hasn't been reliable. It just does what it should. You can connect up the pins and use them as outputs to control loads. You can use them as inputs and read from them. So you can use them for, button inputs or sensor inputs or whatever, but it's digital. So with the MCP23017, that's good for digital mode I/O. For things like driving PWM, I've been using the PCA9685, which is once again, I believe it's 16 channel. It's definitely at least 8 channel, but I think it's 16 channel. So it's a 16 channel hardware PWM driver chip, and it's designed specifically for driving LEDs, but you can also use it for generating PWM for other purposes. So if you want to modulate some kind of a signal, you can connect to the PCA 9685 using I2C, send it a command, and give it a couple of parameters. One is the frequency of the square wave that's going to come out of the output. So you could set like a base frequency of 100 hertz or a kilohertz or whatever. Kilohertz. Hertz is not singular. A kilohertz. So you give it the base frequency of what you want the square wave to be, and then you give it the duty cycle, so the percentage of the square wave that will be high versus low. And so what you do is set the base frequency for a block of outputs. I think it's 8 in a block. And then you set the duty cycle on each of the pins individually. So where I'm trying to drive PWM on I2C, I normally use the PCA 9685. And one other common thing that a lot of people do is use something like a little ARM processor. I know John Spencer, who is here in the chat, I'm pretty sure he's done this in the past. Like, he's worked on projects where he's put on something like an ARM Cortex M0 as a secondary processor and used that to connect some I/O. I think he did that on a project that he was working on with Rob from the Hackerspace. Okay, so Scott said, how about an I2C ADC? Yes. What did I do that on recently? You know, one of those brain isn't quite working properly moments. I did use an I2C ADC on some project. What was it? It has totally gone out of my head. No. I think I might be misremembering. What I'm thinking of is the ADC used for load cells. And the protocol they use is kind of like I2C, but it's not quite the same. So I'm just going to have a quick look at that. There is, so on the Zero stick, which is the zero deflection joystick for assistive tech projects. Let me see. HY, yeah, so the part I used on that was an HX711, which is an ADC that uses some kind of a, I can't remember the protocol. Anyway, it's a little while actually since I've looked at this, so I can't remember the details. But I'm sure I've used an I2C ADC somewhere else. The part number is not in my head. It's been flushed from cache, and I would have to go into, I'd have to look at external storage in order to refresh my cache and get it back into my brain. So sorry, I can't answer that one. I know I have used I2C ADCs in the past, but cool. So Sion's got a suggestion, the ADS1015. It's an I2C 12-bit ADC. Cool. Yeah, and the ADS1115. All right, cool. I haven't used that particular part, Sion, but that's interesting to know. So hopefully that will help Scott. And I'm going to have to look into the ADS1015 because that could be a very useful building block. That's one of the, I don't know, just a little observation. What I find is a lot of what I do in terms of design is reusing building blocks. And it partly comes down to familiarity with specific parts. So if I want to do switchable GPIO on I2C, I will reach for an MCP 23017 because I've used it so many times before. I know how it works. I've got proven footprints. I can slap it down on a PCB and I know that my footprints are going to work. I know the driver code is going to work and it's comfortable. I'm sure there are other solutions to it. There are many other chips that you could use as I2C GPIOs, but because I've used that part, that's what I tend to reuse. So in a situation where I need something like an I2C ADC, because I've done that very rarely. I don't really have a go-to solution for it, and I'd have to dig into what it is. But over time, as you work on more and more projects and you find that you need to do certain things, you end up building up more of these go-to solutions for these specific problems. And then when you're working on something new, you get a situation where you need to read an input, and you've got to do analog, and you need a whole bunch of them. So you need something like an I2C ADC so that you can have a few of them. Then you solve that problem, and then if you ever face that again in the future, you already have the solution. It's in your mental toolbox, and you've probably got parts left lying around from the previous project, and so you've got samples and you've got known footprints and all of that sort of thing. So one of the things I find interesting is just as I've worked on more and more projects over the years and developed these little solutions to problems that I come across, it means that when I start on a new project, I've got a bigger toolkit that I can bring to bear on it and solve the different parts of the problem. Alright, I think I am going to stop because, as you've been able to tell, my voice hasn't been doing too well today. I don't know why that is. I actually feel fine. I'm a little bit tired, but I don't feel sick or anything. It's just my voice has not been doing so well. Okay, so I'm gonna sign off for the day. Well, for the live stream. And thank you very much for coming along. This has been really cool. Yesterday I was wondering what I was going to talk about, and when the thing about the ESP32 pinout came up on Twitter, I thought, yes, that is actually an interesting topic, and hopefully useful to a few people. So if you do ESP32 projects, check out that spreadsheet, and if you've got suggestions for it, please send them to me. I think I am going to expand that spreadsheet, add more columns. I'll add pins for different modules, not just the Vroom 32, because sometimes it can be useful to have the pin listed for whatever module you happen to use. What I would like to do, the thing is the different modules have different pins broken out, and indicating that could be tricky. I'll have to think about that. It might be worth having multiple sheets in the same spreadsheet and one sheet for each module. So we could have a sheet in there for something like the Tiny Pico, and a sheet in there for Vroom 32, and for whatever else. You know, things like that. Even the ESP01, which is a tiny little module. It's only got a couple of pins exposed on it, but it could be useful to look at that and know what the capabilities are of those pins as well. But being able to filter the spreadsheet to just the pins that are exposed on the board that you care about, that could be a little bit tricky. Anyway, I will see if I can come up with a solution to that. So, okay, it looks like I'm getting some more messages coming in through the back channel. Oh, interesting. So the suggestion was to add the ESP32 I2C go-to IO expansion options on a second sheet in the pinout spreadsheet. That is a very interesting idea. So what I could do, just thinking through that, so extra sheet, and I could have some options like list the PCA 9685 and the MCP 23017, and as Sion suggested, maybe the ADS 1115 and the ADS 1015 as options, and maybe some suggested pin connections or something, so that if you're looking at the pinout on the main spreadsheet and you say, oh, I don't have enough PWM outputs, then you go to one of the extra sheets and it will show you how to connect an expanded PWM output driver. That is a very cool idea. Thank you very much for that idea. All right. Okay, very last thing. Mr. Absolute Soul said, before you go, can someone give me a quick rundown on how to use Discord? Okay, so the Discord link, I think it was put in somewhere earlier in the chat, but I will put it in again now. Please excuse me while I'm typing. So Discord is a chat system. Yeah, so as James said, follow that link and sign up. And Discord is interesting because it's like somewhere in between a live chat system and a forum. So with a forum, you put in a post and then you go away and then you come back like a day or hours or whatever later and see if anyone has replied to your post. Whereas with Discord, it's more like live chat, but grouped into little areas. It's a little bit like Slack, I suppose. Pretty straightforward to use. So if you just follow the link and yeah, as DIY in the Ghetto said, oh, I think, yes, I started misreading that. Yeah, thanks for coming along and checking out the dodgiest backlit logo in the world. And I will see you all really soon. Have a great Sunday afternoon. I'm going to take a swig on a drink and clear my throat, hopefully. Right. Good night, goodbye, good morning, whatever is appropriate.